So, as the title of my talk presents, I'm going to talk to you about music, evolution, and cheesecakes. Music is very much a sort of an enigma. If you think about it, you can ask yourself, how is it that sequences of tones, which are pretty much meaningless, create such strong emotions in us? So people report they feel changes in breathing, shivers, goosebumps. They sometimes even have tears, out-of-body experiences, a whole bunch of responses that it's really difficult to think why they are evoked by sequences of sounds. Of course, music has been used for a variety of activities from very early on. One of the most consistent uses of music in various traditions is in ceremonies, especially in attempts to communicate with the superpowers, with gods, with the good spirits, with the evil spirits, and what have you. Of course, you cannot communicate with the gods with regular speech, so you need something that is special. And music is such a special sort of communication. Other activities involved in which music is involved with are mostly social, so ceremonies. Again, may be related to religion, but also could be related just to social activities. This is true of today as it was before in early ages, of course. Be it in weddings, in social gatherings, mourning the dead, on the other hand. So it has something to do with social communication as well, not only with the supernatural, but some power to give us the feeling of a coherent group. And we may talk about it a little bit later. Music has been used to change our level of arousal. You know it again from your own experience. When you want to energize yourself, you put the music you like, which is energetic, and then you do spinning or running or whatever. And it also helps to reduce arousal, to make us more calm. Maybe the extreme example is lullabies that mothers used to, mothers and fathers used to calm their babies with. It's been used as a mnemonic aid, so it helps us remember things. It's not only jingles that we remember, but think about songs for learning the ABC. Think about prayers, think about narratives that actually maintain the memory of a social group. When there is no writing, it's all remembering by heart, and music can be very helpful in that domain. As I said, giving us a sense of a group. For one thing, connecting all the people who are singing the same song or dancing the same dance. And on the other way around, disconnecting this group from another. So creating boundaries between one social group and another. It's very useful as a tool for rhythmic entrainment when people have to act together, for example, in work songs. So it's very useful then. Marvin Minsky had a very nice idea that music is sort of a very nice tool to teach us about time. So like a child, he's playing with cubes and trying to figure out space around him. And so we use music as a way to learn about time organization, since time is a very tricky thing. It's not perceived in any regular sense. So that's another idea. Anyway, there are a whole bunch of ideas why we use music, and this is not what I'm going to talk to you about today. I just wanted to give you this larger framework, but I want to focus on a more specific question. And this is the question. Are we a musical species like some people have suggested? Are we pre-wired for music just like we are for language? So this is putting music in a different, even stronger perspective. And anyone who read the introduction to Oliver Sacks' Musicophilia, I think in the first few pages, he says, we are a musical species. And what I want to convince you today that even if the answer to this question is no, and that's going to be left somewhat open, the mere posing of the question is interesting and leads us to think about interesting questions regarding to music and brain and evolution. So this is the route I want to walk through with you today. We can ask, how did musical ability come about? Not only for what, but how did it develop? And of course, the ultimate question can be, if it does have any biological roots, what is it good for? Steven Pinker, in his book in 1997 on how the mind works, has a very nice way of tackling this question and posing it. This is how he puts it. In all cultures, certain rhythmic sounds give listeners intense pleasure and heartfelt emotions. What benefit could there be to diverting time and energy to the making of plinking noises or to feeling sad when no one has died? And he poses his answer, which is actually that music has no evolutionary or biological importance. As far as biological cause and effect are concerned, music is useless. It shows no signs of design for attaining a goal such as long life, grandchildren, or accurate perception and prediction of the world. Compared with language, vision, social reasoning, and physical know-how, music could vanish from our species and the rest of our lifestyle would be virtually unchanged. So this is taking a very strong claim, saying that music, in terms of our species, could disappear and nothing significant would happen to our human species. It's not on the individual level. I'm sure there are some people here in the audience that if music would vanish from their lives, it would make a hell of a change. I can tell you about myself. But at the level of the entire species, that's an interesting thought. And when you think about it, it's really quite a difficult claim to make the other way around. That is, that music does have biological causes and roots. But let's see what Pinker suggests. He says that music making and listening, and that's why I said musicking and not just music, is parasitic on other useful mechanisms. So it's not that we have developed special mechanisms for doing music or listening to music. It's just that, fortunately, we use pre-existing mechanisms in a very intelligent or creative way to make music and enjoy it. So one thing he proposes is that we use auditory scene analysis. I assume most of you know what it is. I'm going to repeat a little bit what it is and especially give you some examples. So, of course, music is about sound. And one thing we do when we process sound is distinguish among the different objects that we have in the scene, just like we do with vision. So in 1990, Al Bregman, in his book Auditory Scene Analysis, drew an analogy between what we do in vision and what we do in audition, in the sense that we have to parse the surrounding into edges, surfaces, objects, and that's what we also have to do, not only in vision, but also in our auditory processing. So usually there is more than one single source at a time, and what we have to do is to be able to distinguish these sources. In this hall, for example, you hear my voice going on, blah, 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 blah. Hopefully it doesn't sound like blah, 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 more intelligent than that. But you may also hear some consistent noise of the, I don't know, speakers, someone moving alongside you, and so on. And you have to be able to connect all the sounds that come from my voice to a single stream and differentiate them from other sounds. And actually music plays on it a lot, especially polyphonic music, so when we have more than one voice, but whenever you have two people singing or one voice and an instrument, we have to do that in a very significant way. So auditory scene analysis is going to be one process that we're using heavily in music, and in a moment I'll train you to do it more in a specific way. Pinker suggests we use other mechanisms that actually derive from language processing. I'm going to go back and forth touching upon the connections between music and language as we go along. But just to start with, you can think about the intonation in speech, all the musical aspects of speech. When I talk to you, you hear the words, but you also hear a modulation in the frequency of my rising and falling voice. Maybe my intensity goes up and down. Rhythm, I talk maybe a little bit faster, slower, and all these aspects are, of course, what we do with music. For example, Jocelyn Lauka, in a nice paper in 2003, compared what instrumentalists do when they are asked to play a piece in a specific emotion, say play the piece so it reflects sadness or happiness or anger, versus what people do, or actually actors do with their voice when they're asked to do the same. And they found that the modulations in the acoustic parameters are very similar. Which is not surprising, but it can give us one hint how music affects our emotions. If it mimics what we do with our voices in general, it might be one way to transfer emotions to us. Of course, questions like, is it cultural specific or not, come into play. I'm not going to go into this. But not only mechanisms related to the prosodic level, but also mechanisms related to syntax, how we organize the units, maybe in recursive ways, maybe in hierarchic ways, and so on. Pinker suggests we may be using our ability to process emotional calls. Another aspect is motor synchronization and entrainment to rhythmic stimuli, which is something that we do. It's most obvious in music, but it's not only there. For example, you have very nice examples of synchronization in mother-infant interactions. When you film the interactions and look frame by frame, you can see how synchrony comes into play in terms of the sounds and the gestures of mother-infant. And so this might be something very basic to our ability to learn from our surrounding, and it's, again, capitalized on in music. This is what Pinker suggests. And this is where the cheesecakes come in. Music appears to be a pure pleasure technology, a cocktail of recreational drugs that we ingest through the ear to stimulate a mass of pleasure circuits at once. So maybe this is what music is all about, at least according to Pinker. One thing that I think comes through in his chapter that I have been citing from is that he thinks about music in a very different way from what I would suggest you should think about music. He thinks about music like music is today or has been for the last 300 or 400 years. And of course, this is a very limited way of thinking. And he talks about music as sort of activity that you have to learn. You have to go to your violin teacher and she has to show you what to do and to tell you which notes to play. And again, this is a very westernized, limited way of thinking about music. When we're talking about music in an evolutionary perspective, of course, I have no idea how music sounded 40,000 years ago or 200,000 years ago. But if one thing I can be sure of, it didn't sound like your regular, what you have on your iPhone or iPod or whatever, no? I want you to think about it more along these lines. Maybe we'll listen to the example and then we can, I'll point to a few things.
The Aka-pygmies, who live in the southwest region of the Central African Republic, have developed a vocal musical tradition that differs radically from those of neighbouring ethnic groups and can be found nowhere else on the African continent. Music and dance have long been inextricably linked to all social and cultural events within the Aka community. They form an integral part of Aka rituals, including ceremonies related to the inauguration of new encampments, hunting, assemblies of several encampments, and funerals. This extremely complex type of contrapuntal polyphonic singing is based on 4 voices. Unlike polyphonic systems that are written down using notation, the vocal tradition of the Aka-pygmies allows for spontaneous expression and improvisation. The community has elaborated extremely complex musical forms. During performances, each singer can change his or her voice to produce a multitude of variations, creating the impression that the music is continuously evolving. The songs are generally accompanied by various percussion and string instruments, each one played for a specific occasion.
Okay, I'm going to stop here.
Used handcrafted instruments are a local type of tom-tom in Zeko, a harp-like instrument known as a guidala bagongo, and the single-string bow.
Okay, I'm going to stop here.
The songs perpetuate.
And this gives you the flavor of what I mean. Music is part of social life. It's not something you have to learn to go to a teacher. It's something that you sort of drink and eat daily. You can also see a couple of other components in here. It's a social activity. It involves a number of voices, at least in this group. These voices are usually pretty simple. I mean, each participant repeats a pattern which in itself is pretty simple, but the combination of the patterns creates a complex texture together. You can also see it's multimodal. It's not music really. It is dance and ritual as one package. It's not detached from life. It's not that you go to an auditorium and you just get music. You have it within the social fabric, combined with dancing and with rhythm and with rhythmic activity and motor activity involved as well. And this is the type of music I want you to bear in mind when we're talking about the evolutionary roots of music. Okay, I wanted to give you another example of polyphonic music, a very different one, and test your ability to do auditory scene analysis. So this is also polyphonic. When I say polyphonic, poly is many, phonic is sound, so it has many voices in it, not just a single singer who is singing, but we are combining the voices of many performers, and each one has a melody of its own. That's the complex thing about this thing. And what I want to show you now is first to give you a feeling of what I mean auditory scene analysis, and then to show you how much the visual information and other information is also relevant when you do the auditory scene analysis. So just, okay, I'll just say 2 words about the word fugue here. The musical form fugue is based on the idea that you have a repeating melody. The melody is first presented in a single voice, which is very helpful for the listener. Because what you have to do is when the melody begins and you have no other interruptions is really to learn the melody, because what you're going to do next is to try and find it whenever it repeats. And at least in the introduction of this musical form, we have a very regular way of appearance of the melody. So it appears first without any accompaniment, and then it repeats itself, and the second voice enters on the top or above this melody in a counter melody of its own, and then usually you have another entrance, or you have an episode where the voices sing something else, akin to what you have already heard, but not the thing itself. And then the third voice introduces the melody, and so on. And along the piece, you will hear repetitions of this melody. Another thing I want you to notice is that the repetitions are not exact. If I tell you the notes or the frequencies of the melody, it usually doesn't repeat the same frequencies. It is shifted. So what we have here is something that's called relative pitch. We are not so much interested in the absolute frequencies of the tones, but in the relations among them. So whether I went up or down and how much I went, that is what is going to count when we decide that a melody is similar or different from another melody. Okay? And I want you to bear in mind when we proceed later on. So here's a pretty well-known example. Here it's in the Swingle Singers version. And this is the melody you have to remember. Okay, we have the melody and another tone. Now an episode, and then the melody again. Can you hear it? But it's not, it's just okay, it's pretty difficult. It's not trivial. I want to help you now with a visual aid. And this is what I want you to, we will just see, but I just want to remind you that I said music is not only sound, it's about sound sources and about a full interaction with the vision, with the motor aspects of it, and so on. So here's the same thing. It's going to be much slower, and you'll have a visual aid to help you. Darker green. Red. Now I'm sure you can distinguish much better the different voices. Not only the melody, but even the inner voices, which are more difficult to follow. Okay. So if you are going to be bored the whole lecture, at least this part is nice. Okay. What do we want to do next? Of course, I just have to say a few short words that are necessary at this point, that music is, of course, a cultural phenomenon. No one is saying it is not. And one thing you might find surprising is that we don't really know what music is. I mean, we don't agree. There is not an agreed definition what music is. In terms of etymology, the word musicae comes from the Greek, and it relates to the 9 muses, the arts and the sciences. And from there on, the word goes, and it first appears in English in the Oxford Dictionary of English in the 13th century. And this is one definition that you have in that dictionary. That one of the fine arts which is concerned with the combination of sounds with a view to beauty of form and the experience of emotion. Also the science of the laws or principles of melody, harmony, rhythm, etc., by which this art is regulated. But the whole story I was telling you before that about the social role of music, it doesn't come into play in this definition at all. And indeed, in some African tribes, you don't have a word for music. The word always means music and dance, music and speech. There is no word for music. Or you have cultures where you have different words for secular music and sacred music, for instrumental music and vocal music, not a specific or general concept covering the whole thing. So here's a nice citation from Zaire. When you are content, you sing. When you are angry, you make noise, probably speak, no? A song is tranquil, a noise is not. When one shouts, he is not thinking. When one sings, he is thinking. And so this is another way of looking at music. And one of the nicest definitions I found, and it's not that I recommend to go to the Wikipedia for everything, but for this concept, this is a really nice entry there. And I'm going to read it through. The definition of music is a contested evaluation of what constitutes music and varies through history, geography, and within societies. Definitions vary as music, like art, is a subjectively perceived phenomenon. Its definition has been tackled by philosophers, lexicographers, composers, teachers, semioticians, semiologists, linguists, scientists, and musicians. Music may be defined according to various criteria, including organization, organized sound, for example, pleasantness. So we saw in the definition before, it had to be nice. Intent, social construction, perceptual processes and engagement, universal aspects of family resemblance, and through contrast or negative definition. One of the nicest definitions I know is that music is a form of communication that is not language, which is nice. Of course, I'm sort of exaggerating, but in general, there is no, you have to accept that even the word music is sort of ill-defined. So, what we are asking is, could music have some adaptive value? And once we pose this question, I think that out of this fall out a bunch of questions which are getting maybe more interesting. So one thing, it must be universal, and indeed it is. There is no culture that doesn't have some form of song or song plus dance, and so it is universal. And the next thing we want to ask is whether in all of these diverse musics, and I won't take the time to give you examples, today with the YouTube you can open and hear various types of music from all over the world, but we can ask whether there are any universal musical features common to all of these musics, maybe akin to universal grammar that Chomsky proposed for language. There are some. None of these features is universal without exclusion. I mean, for every example I'm going to give you, you will find a counterexample. But in general, For example, most music in the world have a special status for the interval of octave. The interval of an octave is what we naturally do when we sing, each one in his own range of voice. So if I sing a very high voice like ah, and you have to repeat it, and maybe some of the males here cannot reach that tone, they are going to sing the same tone, but in a different, in an octave. So it also physically is the proportion of 2:1. It's the first overtone in the overtone series, so it does make sense that it has a spatial status. And in music, you know that, or maybe you don't, and you should know that tones an octave apart receive the same name. It's not only in the Western system, but in most musical systems, when you reach the same tone and it reaches the octave, it receives the same name. And this is very useful because we represent a whole bunch of frequencies in a limited number of categories, and of course cognitively it is very important. So the interval of an eighth and a fifth are used in many musical systems. You can talk about the number of tones in the scale. So the fact that you have scales is one thing, and that you have a limited number of tones in the scale is another example of universal, and so on. I won't have time to go into this, in this talk, into all the features, but just to give you an idea that this is something people have been talking about, looking for, and discussing quite a lot, with just a very limited number of common musical features found till now as really common to all musical systems. Well, it has to be pretty ancient if we're talking about evolutionary time scales. We want to know how ancient it is. What we do know is, of course, we don't have any recordings of sounds going back way back, but we do have these flutes found in southwest Germany that have been dated back to 35,000, maybe 40,000 years ago. So you can see how beautifully this instrument is prepared. And they found a couple of flutes there made from bones. So you can imagine that if by 40,000 years ago there were already musical instruments that complicated as this one, and a number of those in this same area, music by singing, clapping, and other instruments that didn't survive must have gone way back. Possibly 200,000 years ago, but it's difficult to say how ancient it is. Another feature we want music to have, that it would be easily acquired, so you don't really have to teach someone how to sing. If he's exposed to singing, he is going to sing, he or she is going to sing. And we want to see clear and regular developmental stages, which we do. For example, beyond babbling, you can see later on at the age of 2 or 3, babies repeating the contour of the melody pretty consistently, and some aspects of the rhythm, but they're off in terms of the exact intervals. By 5 or 6, they usually sing pretty well the intervals, but don't have a very good sense of the scale. By 7 or 8, they already know what the scale is, and so on and so forth. So we do have mapped quite a consistent map of developmental stages, with the caveat that whatever I'm talking about here mostly is going to relate to Western listeners, because this is where most of the studies have been done, and maybe we will see some other pattern in an African tribe. Like language, we want to ask, is music human specific? And this is going to be a bit difficult because I'm not going to define what music is, so how am I going to claim whether it is human specific? I'll try to convince you about some things that have been tackled. Are we born musical? Is there any genetic basis for musical abilities? Is also one question we want to answer if we're going to take this evolutionary perspective. And maybe the last question, are there dedicated brain systems for processing music, or does music rely on brain circuitry that's out there for other things? I'm not going to be able to touch upon all of these aspects, some of them, and to some degree. This is what I want to do in the next minutes. So of course there is complex vocal communication in animals, and in some species it's really complex and it gets the name song. Some of you may know about this more than I do, but songbirds, dolphins, whales, rats are a few species in which songs have been identified, and there is a lot of work on the structure of these vocalizations and their purpose. It's interesting to note that already Darwin, in his Descent of Man, drew an association between what happens in the animal kingdom and music. It appears probable that the progenitors of man, either the males or females or both sexes, before acquiring the power of expressing their mutual love in articulate language, endeavor to charm each other with musical notes and rhythms. So Geoffrey Miller, in another book, Origins of Music, sort of followed up on this idea and tried to show how music could have evolved, just like in songbirds, as some form of indication of fitness. So we know that in birdsong, the males that sing more loudly, longer, more complex songs can have really an evolutionary advantage, and he proposes, so Geoffrey Miller following Darwin, that the same is the route, this is the route how music developed in the human species as well. You can debate that, but that's an interesting sort of notion. But what we want to ask is not so much about whether music developed as a form of charming the other sex, but more so whether there are any unique musical abilities or musical abilities that we see in humans that we don't see in the animal kingdom. And this could be an interesting sort of way of showing that music is human specific or could be human specific. For a long time it was thought that one thing that we do and animals cannot do is entrain and synchronize to music. Of course, animals have excellent motor abilities and they move rhythmically. So it's not about moving rhythmically, it's about altering our motor system to accommodate an external rhythm. So the most clear evidence for that is what we do when we hear music and we tap or nod our hands or clap or whatever. Babies synchronize to music, or I should say infants, by the age of 4, they do it very well. And if they're not tapping to a drumming machine, but tap with another person, so drum with another person, they do it even earlier, by the age of 2.5 or 3. So once their motor system is developed enough, they can show synchronization. And it was long believed that this is not seen at all in the human kingdom. Until a few years ago, Ani Patel came out with a story about Snowball, which some of you may be familiar with. Let's see what Snowball does. Okay, you get the point. So the interesting thing was not that he's dancing so beautifully, which of course he is, but that when you change the tempo of the song, no, I don't want that. I want that. When Ani Patel and his group changed, they wanted to see whether Snowball could synchronize when they changed the regular beat of the song. So they increased the tempo by 20% or decreased it. So it was either going faster or slower than he was usually hearing it. And they then framed his dancing, and they could show that he did he did entrain rhythmically, not all the time, not perfectly, but that was clearly that he was able to do it. And I must tell you that for a long time I had the notion that people entrain to music very easily, until I did an experiment a few months ago for a different purpose. But anyway, I had subjects just tap along music, but that was music that was expressive. So the pianist went faster and slower like we usually do. And entrainment wasn't that good. It wasn't all the time, and it wasn't perfect. Maybe a little better than Snowball, but it wasn't perfect. So I'm convinced that Snowball can do it. And in fact, the notion is now that animals that are vocal learners can do entrainment. So it's not that every animal is going to be able to do it, but only vocal learners. And that makes a lot of sense. Because I think that this is the action perception loop. Okay. Didn't do anything. Okay. So shall I try this again and see if it works? No. It's the action perception loop that is probably driving this ability. So you have to hear, you have to have some ability to perceive the sound, and then when you perform it, you want to have some feedback about how well you did, and you have to maybe synchronize to what the other person or other birdsong is doing, and so it makes sense, at least to me. Another ability that seems to be very pervasive in humans and very difficult to find, if at all possible, in the animal kingdom is relative pitch. I hinted at it when we heard the Bach fugue. The idea of relative pitch, as I said before, is that we don't really care about the absolute pitches. I could sing a song and you would recognize it, even if it's very different from what you're used to hearing it, say, on a disc, okay? We do have some sense of absolute pitch. There is a subgroup of people who are called absolute pitchers. I'm going to talk about them a little later. All of us have a little bit of memory for absolute pitch as well. How do I know that? Levitin did a nice experiment in which he asked people to bring in the discs they listen to a lot, and he told them, now please sing song number 3. And people sang the song in the exact pitch, which is usually something we don't know. So it's something that is coded. But we usually use relative pitch, okay? And here is another example of what I mean relative pitch. This is a quiz. Do you recognize this? And let me know if you hear something funny going on. So now I know if you listen in the first part. Now it shifted an octave. Okay, it's the same thing, an octave. Now it shifted again in another interval. Good. Another shift. Okay, you're attentive, very good. So how do I know that you did the transposition right? Because you heard I inserted a mistake in there. So you do the transposition. You take the whole melody and you shift it to another set of pitches. So the absolute pitches are not important. What is important are the relative pitches. So what we are coding are at least two domains or features. One is the up and down. So is the melody going up or down? And we're also coding how much is it going up or down, okay, the proportions. I already talked about octave equivalence, that we name tones an octave apart as the same name, meaning we sort of hear them very similar to each other. I think we're going to close this part with another fugue. You're going to come out of this lecture experts on fugues. And what I want you to note here is how we use these transpositions not only to transpose the whole melody, but also subsections of the melody. So what we call in music sequence. Da, 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 da. So it's the same sort of pattern. It's not the same absolute pitches, and we use it again and again and again in music. It enables us to have a very good notion of what's coming next, because once you understand the pattern, you can apply it to the next time I begin the pattern, and that's where the composer can play tricks on us, and on the third repeat, like I did in my example, insert some fancy deviations. Okay, so we'll take a break in a minute. But notice the repeating patterns here. Look at the orange. It has these sequences. Orange sequences, also in the purple. Our melody. As I said, and I think you experienced very easily, we do transpositions of melodies very easily. It's something very natural for us. And the question now is, how good do other species do the same task? Generally, it's been very difficult to find animals that do not use, or I should say the other way around. All animals use very heavily absolute pitch. This is true of bird songs and of monkeys and primates and what have you. The question is, can they be taught to do and to hear relatively as well? Not only use absolute pitch, but use relative pitch. In the 1940s, there was one paper claiming that rats have octave equivalence. That paper had been criticized on terms of methodology. It wasn't replicated back then. And since then, there have been some attempts to teach birds and monkeys to do, to transpose or to perceive transposed melodies and see if they conceive of these melodies or perceive of these melodies as same or different. And this is a paper by Wright and colleagues showing that it is possible to train. In this case, these were 3 Japanese macaque monkeys. And the way the experiment proceeded was that first they were taught the notion of same different with natural sounds. And then they were taught to do a differentiation between same melodies and different melodies that repeated over and over, where same melodies were kept using the same frequencies, and different melodies use different frequencies, which you can do if you are using absolute pitch, and that's perfectly well. Now, the important part was the test phase, where you had the same melodies transposed by 1 octave, or transposed by half an octave, or transposed by an octave and a half. And at first, they failed to show any octave generalization. You can see here that if you use the same melody, but transpose it by 1 octave, that is, now the frequencies are going to, the absolute frequencies are going to be different. Monkeys are around chance. But that was a very interesting point when they switched to different melodies. The first melodies were random melodies without any constraints of about 6 to 7 notes. In the next round, what they used were melodies with some constraints of repeating and begin and repeat, begin and end in the same note. They made the melodies much more similar to children's songs. And interestingly, this time they did get octave generalization. So from this interesting study, we learned 2 things, that monkeys, after training, can do octave generalization, and that it's also important what you present to them. And there might be some limits of memory, limitations of memory, that our melodies sort of capture and help us remember better, and that's what you have to use when you do these experiments. However, no generalization was shown for half an octave or an octave and a half. So this was very specific to the interval of an octave. And one other thing I am stressing, it took quite a while to train the animals. So it's not something that animals do very easily or very naturally. You really have to push them towards that. And I think this is one important difference, or one feature that we have to remember when we ask whether music is human-specific. Well, maybe not all music, not all aspects of music, but this seems to be a very special thing in the way we construct music and use music. And so this is interesting. Another question that has been asked is, do animals first distinguish between consonance and dissonance? And if they do distinguish, do they prefer one of the 2? For those of you who don't know what consonance and dissonance is, listen to these 2 melodies and you will know. This is the first, now the second. And you can pay me when you want me to stop this one. Am I going to be cruel? Yes, I am. Okay. So now you know what consonance and dissonance is? Yes, you do? Okay. There are two features related to this notion of consonance and dissonance. Two aspects of this phenomenon. One has to do with roughness or beating. So when the frequencies are close by, the auditory system is not able to tease out the two frequencies, and there is interference, and phenomenologically it feels like it's rough and it's unpleasant. At least that's the way we talk about it in Western terms. This is one aspect that's been proposed by Helmholtz already in the 19th century, and it holds. The other aspect of consonance and dissonance has to do more with the consonant part, whereas roughness relates to the dissonance. It can tell us something about the dissonant part. Harmonicity, or in other terms of Stumpf, for example, talked about fusion, has to do with the fact that the two constituent tones of the interval sort of merge. Let me show you this figure where you can see that in this is a consonant interval, and the proportions of the tone are 3 to 2. So like an octave was, the frequencies are 2 to 1. In the fifth, which is the next tone in the series of the harmonics, the proportions are 3 to 2. And you can see that the blue line represents the higher tone. It repeats 1, 2, 3, 4, 5, 6. And the red one is the lower tone, 1, 2, 3. And you can see that they merge. So every now and again, the blue and the red will coincide, creating more a sense of a single tone than two tones. Whereas where you have a dissonant interval, these two tones will at some time, maybe after 15 or 16 cycles, merge, but usually they, or for many cycles, they do not merge, and they give you a sense of separate intervals. So in the Western musical system, there is a lot of talk about consonance and dissonance, mostly because this is one musical culture in which there developed a notion of singing together, and not only in octaves, but in various other intervals. So if you think of the medieval music and Gregorian chants, for example, what you have there is usually at least two tones or two voices, and they move one against the other. And once you have this notion of two tones or two voices moving once against the other, you have to regulate the distance between them so they don't create very rough or dissonant intervals. So there is a lot of talk in music theory, in compositional rules, how to move when you go with two tones and then three voices and four voices, how to avoid the dissonant, or if you are reaching a dissonant, please do it smoothly. You have to have a certain interval going before the dissonant interval, and then after that resolve it. So it is a big notion in Western music, and we talk about dissonant intervals not only as unpleasant but also as unstable. You have the feeling that it cannot stay on that interval. It has to resolve to some other interval. So the question is, first, how basic is this? Since it has to do with the auditory system and the way we sort of code tones, one could think that it is going to be maybe common to other mammalian, to animals, to mammals having the same auditory system. We can also ask what happens in other cultures and maybe in babies. So for one thing, babies do show sensitivity to consonance and dissonance. This is measured, for example, in motion, whether they move, squint in their faces, and so on. And you can see that babies of 4 to 6 months of old respond differently to consonant and different dissonant versions like you heard here. I'm not sure how they got the Helsinki approval for running this on babies, but they did. Another interesting feature that you see, look at the right figure here. In this study by Trainer and colleagues, what they did, they had recurring intervals, say a fifth, but it shifted in frequencies. So a fifth, another fifth, another fifth, another fifth, and then suddenly the fifth changed to a dissonant interval, like a tritone. And what we want to see is whether babies are sensitive to this change. And you can compare that to the reverse condition, where you have recurring dissonant intervals, so a tritone or a minor second, a minor second, a minor second, changing to a third, which is a consonant interval. So are you as sensitive to changes from consonants to dissonance as you are the other way around? You can see here that babies and adults, human babies and adults, are more sensitive to changes going from consonants to dissonance than the other way around. You could think that this has to do with how music proceeds. In music, we usually have a motion from consonants to dissonance. This is more sort of frequent than you have to have many, many dissonants and suddenly a consonance. And that's why checking whether you get the same thing in monkeys, in this case, again, Japanese macaque monkeys, is very telling for us, and you can see the same pattern. So in this case, the monkeys are better able to detect change from consonants to dissonance than the other way around. And so this tells us it is something common. What about preference? So would monkeys suffer like you do here in this room and want to run away from the room when you hear all the time dissonant music? McDermott and Hauser did a very nice study where they had tamarins running around, and they had two cages. So the animals could decide in which cage they want to be. In one cage they had consonant music, and in another one they had dissonant music, and they measured how long the tamarins selected to be in one of these rooms. And this is the result. You can see that humans, like yourself, prefer to be in a room where there is consonant music, whereas tamarins couldn't care less. Okay? So it doesn't seem that it's aversive to them. I must say, though, that they also tested other sounds. Tamarins prefer quieter sounds than louder ones. And in general, they prefer a room with no music at all. So this is one study that showed no preference. A more recent study, working with a baby chimp, did show a preference for consonants over dissonance. So I think this is not really well resolved, and this is something we have to think about. But what I want to stress is not so much the results like the line of thought. This is what I opened my lecture with, telling you that just posing the question of can we think about music in evolutionary terms, and what type of questions fall out from this question, like what is special to music, and whether other species make the same distinctions and have the same preferences. This is what is interesting, not so much the specific result here. I want to show you what happens with a special group of people with a musical deficit, which we term amusics. There is about 3 to 4% of the population who have been identified as amusics, which means they have a deficit in perceiving music. The person who has done a lot of work in this domain is Isabel Perez in McGill University in Canada. And she showed that most of the deficits in this group have to do with pitch processing, not so much with rhythm. They're doing pretty well, or often very well, with rhythmic tasks, But when they have to decide whether two melodies are the same or different, like, for example, we did the transposition and I changed something in the melody, and most of you recognize that, those of you who didn't come to me after the lecture. So musics won't notice that. They often report phenomenologically that they don't like music. It's aversive to them. It sounds like pots and pans, in Oliver Sacks' words, quoting from one music and so on. For a long time, or since Isabel began studying this deficit, at the beginning, she encountered people who had a stroke and then showed deficits in music. Following that, she asked herself whether it can also be congenital, whether you can be born with this sort of deficit. And so she, I think she had an ad in the newspaper in Canada asking for people who feel they have a strong deficit in music. And lo and behold, there were some people who came and told her that they really don't hear anything. I mean, they don't distinguish one music from another. They often sing out of tune and so on. At the beginning, when they tested this group, Perez reported that the deficit is specific to music, which goes back to the question of whether we have specific circuitry dedicated to music. That was a big sort of revelation, because if you have a deficit that is only in music, it probably means something about our brain, and that the brain does have a very, very specific circuit for music. But as years went by and tests became more subtle, you could show that musics do have some deficits in language, mostly regarding the intonation and prosodic level, so the singing of the speech, not so much talking or meaning, but rather how you intone the sentence. For example, if the differences are very subtle, they won't differentiate between a question and an exclamative. You can even see it more directly in populations which speak tonal languages. So languages in which the tone in which you say the word ma means something else, like Chinese, like other certain African languages and so on. So in these populations, you can really test whether our musics are having more difficulties than people who have normal hearing or music processing. And so it's not really clear that it is music specific. Now it's thought that it's much more general. And in terms of the brain, what has been found is that the main deficiency or main indication that you see is not a deficiency or problem in the auditory cortex per se, but rather in the connections between the auditory cortex and frontal areas related to memory. So it is about connectivity rather than a specific problem in the auditory cortex. So it is interesting to ask whether musics differentiate between consonants and dissonants. And what you can see here is that they don't. When they have to relate or to rate the intervals, if they are pleasant or unpleasant, you can see that the minor second, oh, this is nasty. The minor second to the left and the major seventh are rated by controls as unpleasant as compared to most other intervals, whereas for the musics it's much more noisy and there is no such differentiation. Interestingly, the problem is about harmonicity and not about beating. I'm not going to go into the details. This is a paper from 2012, pretty recent, and you can look it up. I think it's very interesting. Okay, are we born musical? We can ask, what do babies know about music? And there has been quite a lot of work about babies' abilities, And I don't want to go into all the details. I can sum up and say that most of the abilities that we show as adults, babies show as well, including relative pitch, including relative timing. So again, if I sing a song very fast or very slow, the absolute timing is going to change, but the relative timing is not going to change, and you are going to have no problem identifying that it is the same tone. So the relativity goes into this aspect as well. Babies, so I said, remember tones, do relative pitch, do relative timing, identify where there are articulations, so where we pause usually. And they distinguish between consonance and dissonance, so they do mostly what we do. What did I want to say next? These are the abilities. One interesting thing is that you do see the influence of culture. Let me play you these 3 examples. So you repeat this melody again and again in an experiment with infants. And after they get used to this melody, you insert some changes. And what you're looking for is whether the infant or the baby perceive this change. Usually perceives means changing where he's looking at. So usually you have 2 speakers, and you want the baby to show that he noticed the difference by shifting to the speaker where the new melody came from. You can also examine heart rate, you can examine sucking rate, all bunch of measures telling us, this is before going into brain measures, telling us that the baby has noticed some change. So you can shift the melody in different beginning frequencies, but when you do this change, you can see that babies detect the change. I'm not even sure you remember the first one. It's pretty close, but it's nonetheless different. For adults, this difference is a huge difference. This means you already have a notion of the scale or key, and when I go out of the scale, your brain is going to generate a really strong response, and you can also have other types of responses. For babies, there is no such differentiation. You can see here the basic mechanism of detecting change, and you can see acculturation, which is the sort of scales you grow into. A similar difference has been found in terms of detecting changes in rhythm. And there you can see that babies in Albania, where they have complex rhythms of 5, are detecting very easily changes in these complex rhythms, whereas we adults raised in Western rhythmic patterns find it very difficult. So there's no big surprise here. But it's nice to see that actually all the abilities that we show in musical listening are there at a very, very early age. Some of the differences or abilities are at really 2 or 3 days of age, and others we can see them coming in at 2 to 4 and maybe 6 months of age. We know infants are attracted to music. It is not by chance that we tend to sing to our babies, and we use lullabies to regulate their mood and calm them down, or play songs to activate them. In fact, if you test cortisol levels in babies after singing as compared to after speech, infant-directed speech, which is the special kind of way we talk to babies, you can see that cortisol drops down more strongly and for longer times after song as compared to speech. Another thing I want to highlight is that when we do talk to babies, and we do it whenever we can probably, we use a special way of speech, which is called motherese. And if you look at the features of this way, of this motherese, it's highly musical. we use high, well-defined pitches. Oh, my darling. Oh, cutie. So I'm stressing the vowels. I'm sitting on them, and then the pitches are clear. I lengthen the vowels. I speak to babies much slower than I would to an adult. I use a lot of repetitions. Oh, cutie, 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 cutie. No, we'll do that. And that's, again, a rhythmic repetition, which is specific to infant-directed speech. And accentuation of emotional gestures, just like I presented at the beginning. It's not about speech. It's not about voice only. It's about motion. It's about touch. It's about vision. It's a whole parcel of thing. And in fact, it has been proposed that the origins of music are not mating and males trying to attract females, but rather mothers talking to their infants. If you think about it, it makes a lot of sense that when one way of regulating the mood of the baby is a very strong way is through voice. And if these features are so close to music, the gap from here to music is going to be pretty short. And here's, when are we done? Like 1:45? Okay. Yeah, let's go for it. It's a nice example. It speaks for itself.
Babies this young are extremely responsive to the emotions and the reactivity and the social interaction that they get from the world around them. This is something that I started studying 34 years ago, when people didn't think that infants could engage in social interaction. In the still face experiment, what the mother did was she sits down and she's playing with her baby, who's about a year of age. And she gives a greeting to the baby gives a greeting back to her. This baby starts pointing at different places in the world, and the mother's trying to engage her and play with her. They're working to coordinate their emotions and their intentions, what they want to do in the world. And that's really what the baby is used to. And then we ask the mother to not respond to the baby. The baby very quickly picks up on this, and then she uses all of her abilities to try and get the mother back. She smiles at the mother. She points because she's used to working where she points. The baby puts both hands up in front of her and says, "What's happening here?" She makes that screechy sound at the mother, like, "Come on, why aren't we doing this?" Even in this 2 minutes, when they don't get the normal reaction, they react with negative emotions. They turn away. They feel the stress of it. They actually may lose control of their posture because of the stress that they're experiencing. So the good, the bad, and the ugly. The good is that normal stuff that goes on, that we all do with our kids. The bad is when something bad happens, but the infant can overcome it. After all, when you stop the still face, the mother and the baby start to play again. The ugly is when you don't give the child any chance to get back to the good. There's no reparation, and they're stuck in that really ugly situation.
Okay, so I want to cite from a researcher that has suggested that really these are the roots of music. and not only music, but all the arts. I suggested the elements of or operations of communicative musicality as they developed phylogenetically in interactions between ancestral mothers and infants, and this includes simplification or formalization, repetition, exaggeration, elaboration, and for older infants, manipulation of their expectations or surprises, which is something we saw here in the ugly part, which we don't do necessarily that bad usually, but we do play with expectancies with our babies. Or simultaneous vocal, visual, and kinesthetic expressions are the origins of the capacities later used by humans in making and responding to music. Long before adult individuals themselves intentionally began to make what we call music and the other temporal arts, which in small-scale societies are generally performed all together, these operations were adaptive between caretakers and infants, serving to coordinate behavior and emotion, and by so doing, to conjoin or bond the pair. So this is sort of a nice route, different route from what I've taken you through today, and it's worth going more deeply into. I'm not going to do it today. I don't have any more time, but I do encourage you to, for those of you who are interested, to read Alon Diseniaki. Again, many of these papers are bound together in a book called The Origins of Music, edited by Wallin, Merker, and Brown. And if you're interested in this topic, I think this is a good starting point to get acquainted with this field. Is there any genetic basis for music abilities? Well, one aspect or one way to look at it is to look at kinship among musicians. So do we have ancestries of musicians? And one of the most well-known ancestry is that of the Bach family. I wrote here 48 out of 55 family members of Johann Sebastian Bach were themselves musicians, either composers or more typically organ players. Does that tell us a lot? Well, not necessarily. We know that in that epoch, music, like other activities, was organized in guilds, and maybe the Bach family was a very strong music guild. Yet you can find other examples, and that's sort of interesting to follow. Maybe a much more strong case can be made in studying twins. And in a nice study by Dreiner et al. From 2001, they compared monozygotic to dizygotic twins on a test that is sort of not the best test I could think of, but they followed an older paper by Kalmus and Fry, and the test they used was called the distorted tunes test. They took well-known melodies, they inserted errors in them, and they wanted to see whether you identify it as the correct melody or you notice that it's somehow wrong. And by comparing responses of, I think they had something close to 140 twin pairs, they could extract the irritability factor of 0.71 or 0.8, which is really, really high. In our study with Richard Epstein, we found an interesting association between genes coding for vasopressin receptors and scores on various musical memory tests. This sort of maybe funny or not very strong finding that we had, since we had only 100 participants, was later replicated in a group of large Finnish family with 384 family members, all of whom went through musical memory tests and were interviewed. And so this is another sort of aspect I'm not going to talk about today, just to let you know there are some attempts towards this direction. Maybe much more telling are these studies. Absolute pitch. I told you that most of us use relative pitch. This is also true of babies, but there is a sub group in the population which have absolute pitch. The definition of absolute pitch, or one definition, is the ability to identify a tone without having before that a reference tone. So if I sing la, and I ask you which tone it is, and it's not la, I just use the la word. Is there anyone here in having absolute pitch? Okay, I don't know if it was off, wasn't off, I have no idea what it is. It's something. And someone with absolute pitch could tell you, well, it's D sharp or A or whatever. Among musicians, 10 to 15% have absolute pitch. In general, it seems to depend on two factors at least. One is early exposure to music, since the way I defined it, I told you, you have to associate the tone with a name. So if you're not exposed to music, you're not exposed to notes, you don't know what D or C sharp or F are, you're not going to have it. At least not in this way of defining it. There are some other ways you could test absolute pitch. So early exposure, and you can see that there are some differences in brain morphology between absolute pitch possessors and regular musicians. I'm not going to go into this part, but I can tell you that there is a correlation between the age you began learning and the changes that you can see in the brain. The time window, the relevant time window for obtaining absolute pitch is until 9, the age of 9. Beyond that, you usually don't get the full-blown absolute pitch thing, with a distinction of two subgroups, blind and autistic. These subgroups can or do possess absolute pitch even if they start learning music later on, which is interesting. I don't have a very good idea why it is, but I think it's worth studying. Anyway, absolute pitch does aggregate in families. As you can see, a sibling that also had early musical training is 15 times more likely to possess absolute pitch than another individual who started as early to train in music but has no family history of absolute pitch. Jane Gittier in the group in University of San Francisco has been looking at the genetic aspects, not only trying to figure out how it's aggregated in families, but really doing some genotype, but they're not coming up with some good results up to now. What they try to show, if you look in their website and look at the Athos paper, they try to show it's a dichotomous ability. So either you have it or you don't. If you look more closely into the paper, you will see it's a weak claim, and it's not as simple as that. Anyway, this is a nice way of tackling the genetic basis, because it seems to be a pretty encapsulated ability or specific ability. And the other part of the continuum are those who have difficulties with pitch, and you can see that also here there is some aggregation in families. And I guess this is going to also be a target for genotyping in the next few years as well. So there seem to be some genetic basis, again, for aspect of pitch, again touching upon this question of absolute and relative. This sort of converges into a pretty nice story there. Okay. I'm going to conclude with one slide and one music example. The slide is going to compare using PET scans the brain circuitry used when you do the following task. You hear a sentence and you are asked to answer the sentence somehow. For example, here the sentence you get is August was the best month for them to take the Spanish course in Peru because, and then you have to come up with some answer. It has to be pretty long because that's the pet constraints in this experiment. Peru was a great place to be that time of year, and the weather was just fine. And then you compare it to an analogous task in music. So you hear the first phrase of a melody, and you are asked to sing, generate, and in this example, Martinez and Brown were interested in also in the generating aspect of things. You have to sing the some musical response. And just to give you a really, really short glimpse, I don't think it's very, very surprising. You get at the top areas that are active when you compare melody generation to rest. These include motor areas like SMA or premotor areas and motor areas, auditory areas like BA22, subcortical areas like the thalamus and insula and cerebellum, and some interesting area that's Broca's area, BA44, 45, and its right homologue. And you can see the same, or you can look at the pictures showing what happens in sentence generation. And maybe what's most interesting is when you look at the overlap between the two circuits or the two nets. And there is pretty much a lot of overlap, which is not very surprising because you have the same mechanism of motor performance, of singing or speaking, and auditory processing. Maybe the most interesting common area is going to be BA 44 and 45, which has been shown to be activated when there are some unexpected chords in a sequence of chords. So when you insert musical deviations, you get activation of this area. And this goes back to the question, does music use specific circuitry for music processing? I'm not sure this really answered this question, but that's a nice way of beginning to tackle this thing. I want to end with this example. And tell me what you make of it later on.
The sounds as they appear to you are not only different from those that are really present, but they sometimes behave so strangely as to seem quite impossible. But they sometimes behave so strangely, they sometimes behave so strangely, 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 so strangely, so strangely, so strangely, so strangely.
Okay. How many of you had the feeling that it began as speech and then became melody? Okay. You should all come to my lab now. So she didn't do anything to the sentence. It's not manipulated in any way acoustically. Okay? It's the same sentence repeated over and over again. Diana Deutsch, this is an example by Diana Deutsch. She's an English woman. She has a sing-song way of speaking anyway. She might have conceived this or prepared this in her mind when she presented the sentence. But it's an interesting question what you have to do to make this shift from speech to language. And apparently it's not that much. And with this example, I conclude my talk. Thank you.